The power behind algorithms. Mastering advanced data structures. Data structures form the backbone of efficient algorithms, enabling programmers to solve complex problems with optimal performance. From managing vast datasets to optimizing search operations, understanding data structures is crucial in modern software development. Whether you're building scalable web applications or developing machine learning models, choosing the right data structure can significantly impact your code's efficiency and maintainability. This guide dives deep into advanced data structures that every serious programmer should know. Fundamentals of data structure design. Data structures are specialized formats for organizing, processing, retrieving, and storing data. They provide a way to manage information efficiently based on different access patterns and computational needs. Designing effective data structures requires considering factors such as time complexity, space requirements, and ease of implementation. These considerations determine which structure will be most suitable for a given problem domain. For instance, when implementing a phone book application, an array might work well for random access but would be inefficient for frequent insertions and deletions. In contrast, a linked list offers flexibility at the cost of slower access times. Time complexity measures how execution time increases with input size, often expressed using big O notation. Space complexity evaluates memory usage relative to input size, critical for systems with limited resources. Understanding these trade-offs helps developers make informed decisions during system design phases. It also enables them to predict algorithm behavior under various scenarios. Exploring tree-based data structures. Trees are hierarchical data structures composed of nodes connected by edges. Unlike linear structures like arrays or lists, trees allow branching relationships between elements. This non-linear arrangement makes tree-based structures ideal for tasks requiring fast searching, insertion, and deletion operations. Binary search trees, BSTs, exemplify this by maintaining sorted order through binary branching rules. A BST node contains three components: a key, a left child pointer, and a right child pointer. The fundamental property ensures all keys in the left subtree are less than the root while those in the right subtree are greater. However, standard BST implementations can degrade into linked lists in worst-case scenarios, leading to O(n) time complexities for basic operations. This limitation motivates the need for self-balancing variants. Self-balancing trees, AVL and red-black variants. AVL trees address the imbalance issue in regular BSTs by enforcing strict balance constraints. After each insertion/deletion operation, they perform rotations to maintain height differences within one level. Red-black trees offer similar functionality but relax the balancing conditions slightly. While still guaranteeing logarithmic time bounds, their rotation frequency is generally lower compared to AVL trees. Both structures ensure O(log(n) time complexity for search, insert, and delete operations. However, their implementation complexity differs significantly due to varying maintenance requirements. Choosing between AVL and red-black depends on specific use cases. Applications prioritizing faster lookups may favor AVL, whereas those needing better write performance could benefit from red-black trees. Hash tables. Efficient key-value storage. Hash tables implement associative arrays where values are stored alongside corresponding keys. Through hashing functions, they map keys to indices within underlying arrays. This mapping allows constant time average case complexity for both retrieval and update operations. Effective collision resolution strategies are essential for maintaining performance guarantees. Collision handling techniques include separate chaining, using linked lists, and open addressing methods like linear probing or quadratic probing. Modern hash table implementations often employ dynamic resizing mechanisms to prevent excessive collisions as data volumes grow over time. Graph theory foundations and implementations. Graphs represent networks consisting of vertices/nodes interconnected by edges. They model real-world situations ranging from social media connections to transportation routes. Two primary graph representations exist: adjacency matrices and adjacency lists. Matrices excel at quickly checking edge existence but consume significant memory for sparse graphs. Adjacency lists optimize storage by only keeping track of actual connections. For directed graphs, we distinguish between incoming and outgoing edges separately. Weighted graphs require additional metadata associated with each edge. Dijkstra's algorithm leverages these weights effectively for finding shortest paths in positive weight environments. Heap structures for priority queues. Heaps organize elements according to heap properties that define parent-child relationships. Max heaps prioritize higher values near the top, while min heaps emphasize smaller ones. These structures enable efficient extraction of extreme values, maximum/minimum, making them indispensable in scheduling algorithms and sorting processes. Binary heaps maintain complete binary tree shapes, ensuring predictable traversal patterns and facilitating efficient construction/destruction operations. Priority queues built upon heap principles find extensive use in operating systems for task scheduling and resource allocation management. Advanced searching techniques. Beyond simple searches, several sophisticated algorithms enhance search capabilities across diverse data types. Tree structures prove particularly useful for prefix-based queries. Tries store strings character by character in a tree-like fashion. Each path from root to leaf represents a complete word, allowing rapid prefix matching and autocomplete features. Radix trees further compress tree structures by merging common prefixes among entries. This optimization reduces memory overhead without sacrificing query speed. Additionally, suffix arrays facilitate pattern matching within large text corpora. Their construction involves creating sorted substrings ending at each position in the original string. Concurrency considerations in data structures. As multi-threaded computing becomes ubiquitous, designing thread-safe data structures presents new challenges. Lock-free approaches aim to minimize contention between concurrent accesses. CAS, compare and swap, operations serve as atomic primitives for updating shared state safely. When combined cleverly, they enable lockless queue implementations that avoid traditional synchronization bottlenecks. However, achieving correctness remains challenging even with low-level optimizations. Memory barriers must carefully coordinate visibility of changes across threads. Software transactional memory offers alternative concurrency control paradigms. By grouping multiple updates into transactions, it provides rollback capabilities when conflicts arise. Distributed systems and consistent hashing in distributed environments. Consistent hashing distributes keys uniformly across servers. It minimizes rehashing costs when adding/removing nodes from clusters. The algorithm maps both keys and servers onto a circular number line. When inserting a key, its placement determines which server handles it based on proximity along the circle. Variations like virtual nodes help achieve more balanced distributions by increasing logical server count beyond physical limitations. Applications range from caching solutions like Memcached to database sharding strategies used by large-scale platforms dealing with massive user bases daily. Evaluating trade-offs between data structures. Selecting appropriate data structures demands careful evaluation of operational requirements. Factors influencing choice include expected data volume, access patterns, and modification frequencies. For example, while arrays offer quick indexed access, they struggle with dynamic sizing. Linked lists provide flexible growth but sacrifice direct indexing capability. Queue versus stack choices depend heavily on desired ordering semantics. First in first out versus last in first out behaviors dictate applicability in specific contexts. Analyzing amortized time complexity proves vital for algorithms involving repeated operations with occasional expensive steps. Skip lists demonstrate this concept through probabilistic analysis. Performance optimization strategies. Profiling tools help identify performance bottlenecks related to specific data structures. Understanding cache locality improves spatial reuse of recently accessed items. Prefetching techniques anticipate future memory accesses to reduce latency penalties caused by cache misses. Spatial locality benefits especially from block transfers in disk I/O scenarios. Memory alignment plays a crucial role in maximizing CPU utilization. Proper padding prevents false sharing issues arising from simultaneous cache line modifications. Compression algorithms sometimes replace traditional storage mediums when dealing with high-volume textual data, trading decoding overhead against reduced memory footprints. Emerging trends in data structure research continues exploring novel ways to handle evolving datasets characterized by continuous stream inputs. Bloom filters exemplify probabilistic data structures optimized for membership testing scenarios. These filters operate using bit arrays and multiple hashing functions. Though susceptible to false positives, their space efficiency makes them attractive for big data filtering applications. Other innovations include sketch data structures approximating aggregate metrics without exact computation. Countman sketches estimate element frequencies within error margins. Quantum-inspired data structures represent another frontier, leveraging superposition states for parallel processing advantages potentially unachievable classically. Practical implementation tips when coding data structures: always consider boundary conditions first. Edge cases often reveal subtle bugs lurking beneath surface-level logic. Unit tests should cover typical scenarios as well as unusual permutations likely to cause failures. Test-driven development encourages writing test suites before implementing core functionalities. Code reviews become essential for catching off-by-one errors or incorrect iterator usage that might lead to undefined behaviors later. Documentation clarifies assumptions made during design decisions, helping future contributors understand rationale behind particular implementations. Common pitfalls and how to avoid them. One common mistake is misunderstanding Big O notation's implications. Just because something runs fast now doesn't mean it'll scale indefinitely with larger inputs. Mismanaging memory allocations frequently leads to leaks or segmentation faults. Always pair allocations with proper deallocation routines regardless of language specifics. Overlooking exception safety during object destruction can result in inconsistent states after partial unwinding of exception stacks. Relying solely on intuition rather than empirical measurements risks suboptimal performance outcomes that could have been avoided through profiling sessions. Real-world applications across industries. Data structures power countless technologies we interact with daily. Social media platforms utilize graph databases to manage friend networks and recommendation engines. Search engines rely extensively on inverted indexes formed via B-trees or tries to deliver relevant results rapidly from enormous document collections. Financial institutions apply priority queues for stock market order matching systems, ensuring trades execute according to price/time priority rules. Healthcare IT systems leverage hash tables for patient record lookups, providing quick access to medical histories and treatment plans during emergencies. Future directions and evolving needs. As hardware architectures evolve toward many core processors, data structures must adapt accordingly. Parallelizable designs gain importance for harnessing increased compute capacity. New programming languages incorporate innovative garbage collection schemes affecting how data structures manage memory automatically. With growing emphasis on privacy-preserving computations, homomorphic encryption introduces fresh challenges regarding secure data manipulation protocols. Ultimately, mastering advanced data structures equips developers to tackle increasingly complex problems emerging in today's digital landscape. Conclusion: from foundational concepts to cutting-edge research areas, advanced data structures play a pivotal role in shaping modern software ecosystems. Their influence spans numerous domains, transforming how we process and analyze information. To thrive in competitive programming landscapes or industry roles, continuously expanding knowledge about these structures becomes imperative. Experimentation with varied implementations fosters deeper comprehension necessary for solving intricate algorithmic puzzles encountered regularly.